I recently made a YouTube short where I synchronized the motion of the potentiometer with a stepper motor. And while I was playing around with it, I discovered that if you stop it precisely in between two steps, I'm having a little trouble getting it to do it now, but okay, there we go. If you get it to stop precisely between two steps, it'll vibrate back and forth and almost be like it's between two of the steps. Now this made me think of microstepping. Now I don't have any sort of microstepping driver. All I have is this crude H-bridge setup that can only drive the coils forward or backward. Just like the accidental vibration glitch, I figured I could use pulse width modulation to control how much current flows through each phase for microstepping. I wrote some code for this little NEMA 14 motor, and then quickly discovered that I didn't have any way to precisely measure how well the microstepping was working. So I switched to using this tiny little NEMA 8 motor that I'd picked up somewhere. I got no clue where it's from, but it's probably from some sort of high-precision optical instrument because it's got a fairly high-resolution encoder on one end and a first surface mirror attached to the shaft of the motor. And the advantage of having that mirror is it means I can measure the rotation of the motor without actually attaching anything else to it. Notice as I turn the shaft of the motor, the little light glint off of it from my light moves along the wall of my desk. And even though there's nothing attached to the shaft of the motor, I'm able to measure the deflection of that light beam. Since both the distance from the mirror to the wall of my desk and the deflection of the glint of light can be measured, I can just use trigonometry to determine how far the motor actually turned. And rather than rely on a fuzzy glint of light from my desk lamp, I'll be using a laser instead. And now I've got it set up and running a routine where it's moving first one full step by full steps, and then one full step by microsteps, and then one microstep. And then it just repeats that in a loop. And you can see it moving right now. No, not very well, because that was the microstep. There's the full steps. There's the microsteps, and now here is the single microstep. You probably can't see it very well because it's so small. Now here's the view from the opposite side of my room, which is about 12 feet away from the mirror. I've taped a ruler to the wall so you can see how well it's actually moving. There's the microsteps. Now here's the full steps and the full step by microsteps. So you can see it's a tad smoother. Now to help with the math, I've drawn a little diagram of what's going on. The laser is shining off of the mirror and then bouncing onto the wall, and the mirror is turning, which affects the path of the laser. And the distance that it's deflected we'll call d, and the distance from the mirror to the wall we'll call x. And the deflection of the beam, the angle at which the beam deflects, we'll call theta b. Now if we assume that this angle between the wall and the lower line is right angle, then by definition the tangent of theta b is equal to d over x. Now in reality, neither of the two angles at the long end of the triangle are going to be perfectly right angles, but because the triangle is so long and thin, we can just assume they are right angles and work with that approximation. It's called the small angle approximation because the angle at which the motor is turning is so small. But once we have this defined, we can solve for theta b. There's one last thing we have to do to get the angle by which the motor turned, and that is divide by 2. Not really sure how else to explain this factor of 2 except by showing you why. Now I'm holding the motor with the mirror vertically, so you can see the reflection off the mirror from my lamp, which is to the right. And notice as I turn the mirror and the light moves. Now the light is deflected by 90 degrees, but I've only turned the mirror by 45 degrees, and it remains the same that the angle at which I move the mirror is only half of the angle by which the reflection moves for any angle. Now that we get the algebra out of the way, I can get to the actual numbers. The x distance, the distance to the wall, which is the same in both cases, I measured it, it's exactly 11 feet. My guess was off by a foot. And the deflection, if you rewind to that part of the video, the deflection for the whole step was 5.5 inches. Plugging that into our equation, we end up with theta m of 1.19 degrees. Now this is a 200 step per revolution motor, so I should have gotten 1.8 degrees, which corresponds to 1/200th of the circle. So that means I was off by only about 33%. With the microstep, it deflected by less than 1 tick mark on the ruler, and the ruler was a 1/16 inch ruler, so I called it 1/32 of an inch because I couldn't really tell even if I zoom into the video, and I end up with 0.0067821 degrees. Now this is I was trying to do 1/64th microsteps, so I should have gotten 0.02 degrees, which is a bit more than I got. So I was way off. So apparently there's something weird going on in my code, or the motor's not behaving, or something, but it was microstepping less than it should have been, which is strange. But at the very least, it shows that you don't need a microstepping driver to do microstepping on a stepper motor. You don't even need a stepper motor driver chip. You just need an H-bridge and a few lines of code. That's all for today's video. Thank you for watching, and see you next time.